Hi everyone. I want to start by going over some symbols with you. I think I've already shown you a couple of these symbols, but I'll just show you the rest of them. These values are all called population parameters because they're all names of values that have been calculated with an entire population, and these values are all called sample statistics because they're all values that have been calculated with a sample. And these are the symbols that are used for each of these values. The symbol for a population mean is the Greek letter mu. The symbol for a population variance is this Greek letter here, which is actually called sigma. It's sigma squared. The symbol for population standard deviation is just sigma. The symbol for sample mean is called x bar. It's just an x with a bar above it. The symbol for sample variance is s squared, and the symbol for sample standard deviation is just s. We won't go over what the symbols are for population median and sample median. I'll just show you these symbols that I already have on the screen. And the symbols for population parameters are Greek letters, like mu and sigma, and the symbols for sample statistics are just regular letters, like well, this is the letter S, and this is X, but it just has a bar above it. So now that we've covered these symbols, we'll go on to talk more about calculating a sample statistic to estimate what a population parameter equals. In other words, we'll talk about calculating a value with a sample, like a sample mean, to estimate what that value would have equaled if it had been calculated with data from all population members. And what we're going to specifically focus on next is calculating a sample mean to estimate a population mean. In other words, we'll talk about calculating the mean or the average of a sample of people to estimate the mean or the average of the entire population that the sample came from. I said that we would be talking about using data from a sample and calculating a sample mean to estimate the mean of a population. In an actual study, a person is usually interested in estimating the mean of a large population, such as a city or even a state or a country. So a person might be interested in recording the incomes of a sample of people living in Pleasant Hill and calculating the mean income of the people in the sample to estimate or to get a rough idea of the mean income of the entire city of Pleasant Hill. That would be an example of using a sample mean to estimate a population mean. So even in real studies, we're interested in learning about large populations of people, but when I do demonstrations of sampling in these videos, I'm not able to put a really big population of people on the screen. For example, I wouldn't be able to fit 20,000 stick figures on the screen. So what I do is I put small populations of people on the screen, and I like to do demonstrations in which I take samples from that small population, just so you can actually visually see sampling from a population. So I'm actually going to do one of those demonstrations with you right now. Here we have a made-up population of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 people. So this is a population of 15 people. Let's pretend that these are 15 students in a class, and we're looking at their 15 exam scores. So this person got a 55 on the exam. This person got a 60. These two people got 65s. These two people got 70s. These three all got 75. We have two 80s, two 85s, a 90, and a 95. So it looks like the exam scores in this class roughly follow a normal distribution or a bell shape, because it peaks in the middle and then it gradually trails off. The mean exam score of this class is 75. And so if you added these 15 exam scores and divided the total by 15, the mean would come out to 75. And it makes sense that 75 is at the center of this population right here, because I said that if the population is normal or bell-shaped, the mean is right at the center. I said that in an earlier video. What I wanted to do in this slideshow is demonstrate collecting data from a sample of the population and then calculating the mean of the sample to estimate the population mean. And I want to show you that typically the sample, when I take random samples from this population, the sample mean will fall somewhere close to the population mean of 75. Close, a little bit, it'll fall pretty close to it on either side. Sometimes it'll end up falling further this way, and sometimes it'll end up falling further this way, but overall, it'll usually be the sample mean will usually be pretty close to the population mean. Because the mean of a random sample usually does a pretty good job of estimating the population mean, especially when the sample size is large. So here I've randomly selected a sample of 3 people to be my sample. Let's pretend that I'm recording their 3 exam scores, and I'm calculating the mean of my sample. So these are the 3 students that I actually ended up surveying. I gave them a survey to ask them what their exam scores were, and I collected data from them. And this is the data set that I ended up recording from them. I added their 3 exam scores and divided by 3 to get the mean of the sample. And it turns out that these 3 people have a sample mean of 75. So their sample mean actually perfectly estimates the population mean. It's perfectly accurate. So let's put their sample mean down here on the number line. Remember that the symbol for sample mean is x bar. The symbol for population mean is mu. Since the population mean is since the population mean is 75, I wrote out mu equals 75. And since the sample mean came out to 75, I'm putting an x bar right above 75. So mu is population mean, x bar is sample mean. And in this case, they're both 75. And I'm going to put the population mean of 75 under here, just so we can see how far the sample mean is below or above the population mean. This will allow us to compare each sample mean to the population mean. Now let's pretend like I'm going to repeat my study. I'm going to go and ask 3 other students what their exam scores were, and I'm going to calculate the mean of my new sample. So now I end up with selecting these 3 students to be my sample, and I record their exam scores. I end up getting 2 85s and 1 95. You can see that this sample comes from the high end of the class, so their average or their sample mean will be above the population mean. These 3 people will probably end up having a sample mean of about 90. So I've surveyed these 3 students, I've recorded their exam scores, and I calculated the sample mean, and it was 88.3. So I'll record that sample mean up here. So this is x bar 1 because it's the mean of my first sample. This is x bar 2 because it's the mean of my second sample. So when a person does a study and takes a random sample from a population and calculates the sample mean to estimate the population mean, the sample mean might end up being accurate, like this one, or it might end up overestimating the population mean, like this one, or the sample mean might end up being too low and underestimating the population mean. the sample that you end up getting actually just depends on chance. So it depends on chance. That's why each time the study is repeated, we're getting a different outcome. So now I'll take a different sample. These 3 people are my new sample. I'm doing the study a third time. I've recorded their 3 exam scores, and I calculate the mean of the sample, and it comes out to 80. So my third sample has a sample mean of 80. And now, let's say I take a fourth sample. That's the mean of this sample. I'm using these arrows to show that just like how the population mean is at the center of the population, the sample mean is near the center of the sample. So you see how the mean of sample 5 right here is pretty close to the center of this sample of 3 people right here. So this sample mean of 76 is about at the center of the sample. Now the reason why the population mean is exactly at the center of the population is because the population is normal and symmetrical. Most of these samples that I'm taking of three people aren't actually normal or bell-shaped. That's why the sample mean isn't exactly at the center of the sample, but it's near the center of the sample. For example, this sample, the mean of sample 6 is pretty close to the center of these 3 people in sample 6. These 3 people have a sample mean of 85 right here. So x bar 6 is the mean of sample 6. These 3 people with 6s are all, they're the 3 people inside sample 6. And if I keep taking random samples, eventually I'm going to get a sample of 3 people from the low end of the population with low exam scores, and the sample mean will end up being too low and underestimating the population mean. For example, these 3 people in sample 11, they have exam scores of 60, 70, and 80, and their sample mean is 70 right here. So these 3 people do kind of come from the lower end of the population, especially this person down here. So that's why their sample mean is down here at 70, and they underestimate the population mean. So if you end up selecting a sample of people from the lower end of the population, the sample mean underestimates the population mean. If you end up getting a sample from the high end of the population, the sample mean overestimates the population mean. But overall, if I keep repeating the study over and over again, and I keep calculating the means of more and more samples, most of the samples will fall, most of the sample means will fall within a certain range of the population mean of 75. Notice how about half of the sample means are below the population mean. About half of the sample means are above the population mean. And the sample means that I'm recording are starting to form a bell shape or a normal distribution, just like the population. And that's actually one point that I wanted to make here, is that if the population is normal, and you keep randomly sampling from that population and calculating more and more sample means, the sample means that you're recording actually build up to form a normal distribution, just like the population. So if the population is normal, the recorded sample means end up being normal. And Now I want to show you an example of what happens when the population is skewed, when the population isn't normal. So here we have another population of students. This is maybe just another classroom of students who took an exam. And in this classroom, the exam scores are positively skewed, or skewed to the right. In other words, most of the exam scores are at the low end. We have 355s, 460s, 265s, and only one person has a 70, and one person has a 75, and only one person has each of these other exam scores. And you can probably imagine that if I keep taking samples from this population and I keep calculating the mean of each sample, a lot of the sample means will end up being low numbers, because if the population did poorly at the exam, a lot of my samples will include students who did poorly, and those samples will have low sample means. So let's take a look at that. In this case, the sample mean is, the population mean is 68.7. If you added all of these exam scores and then averaged all of them, you would get a population mean of 68.7. And now I'm taking 3 people from the population. I've recorded their 3 exam scores, and I'm going to calculate the mean of the sample. And like I said, I ended up getting 3 people from the low end of the population with a low sample mean. I mentioned that that was what's likely to happen in this situation. The sample mean was 58.3. Now I'm going to repeat the study and take 3 other students and record their exam scores. Well, this time the sample mean was about 71. Now I take my 3rd sample. Once again, I ended up getting 3 people at the low end with a low sample mean. It happened again. I got 3 people at the low end. So this is actually going to happen a lot of the time. I'm going to end up getting a sample that includes values at the low end here, just because there's a lot of people to draw from here and not as many to draw from up here. I ended up getting another low sample mean because sample 6 ended up, well, sample 6 includes a 55, a 60, and a 65, and that sample ended up having a sample mean of 60. So when the population is skewed like this, the sample means are piling up at the low end faster than they're piling up at the high end, which means that the sample means are actually going to form a positively skewed shape that looks just like the population the samples are coming from, like this. Once, just like before, the sample means do fall within a certain range of the population mean, but the difference is that the difference between what we're seeing now and what we saw before is that now we're getting a positively skewed shape, and before we got a normal or bell shape. So I'll just scroll through the rest of this pretty quickly. So now I've shown you an example of sampling from a normal population and sampling from a skewed population. And we saw that the shape of the sample means tends to follow the shape of the population. When the population was normal, the sample means ended up being normal down here. When the population was positively skewed, the sample means ended up being positively skewed. But it turns out that the sample means only follow the shape of the population when the sample size is small, which means a sample size of less than 30, typically. If you take large samples from a population over and over, and you calculate the mean of each sample, what actually ends up happening is that the sample means down here end up always following a normal shape, regardless of what shape the population has. So if I took samples of 30 from this population over and over again, and I calculated the mean of each one, these sample means would actually end up following a normal distribution, even though the population is skewed. So when the population, like I said, when the sample size is small, the shape of the sample means follows the shape of the population. But when the sample size is large, the sample means typically always build up to a normal distribution, no matter what shape the population has. And I wasn't able to demonstrate that to you in this demonstration because my population only has about 15 people, so I couldn't actually take samples of 30 from this population. But in the next slideshow, I'll actually show you an example of taking 30 samples of 30 from a population, because generally 30 is the sample size that's needed in order for the sample means to follow a roughly normal shape, regardless of what shape the population has. 30 is generally the cutoff point between the sample means following the shape of the population and the sample means always following a roughly normal shape. In this slideshow, I'm going to be doing another demonstration of sampling from a population. I'm going to be doing another demonstration in which I randomly sample from a population over and over again, and I calculate the mean of each sample that I select. I wanted to mention that in an actual research study, a person doesn't take hundreds of samples from a population over and over again, like how I'm doing in these demonstrations. In an actual study, a person just takes one sample from a population and calculates his or her results with that one sample, and then makes a conclusion about the population. So the reason why I'm showing you demonstrations of repeated sampling, in which I sample over and over again from a population, is to help you understand statistical theory, or the theory of what happens when you randomly sample from a population. It's not meant to show what happens in actual practice. But one thing that these demonstrations of repeated sampling do show you is they show you what happens when different researchers repeat a study and get different results. For example, even though a single researcher might not take hundreds of samples from a population over and over again, it could be that different researchers who are all studying the same population each take their own sample, and they each get different results. And these demonstrations help you understand how those different results that the different researchers are getting have a distribution of their own, in which some outcomes underestimate and some outcomes overestimate, and some outcomes are more accurate than others. For example, if it could be that several different researchers are all interested in the mean income of people living in Pleasant Hill, And each of those researchers takes their own sample, records the incomes of the people in the sample, and calculates their sample mean. And each of those researchers will end up with a different group of people. So each of those researchers will end up with a different sample mean. And some researchers might get a sample mean that underestimates the mean income of Pleasant Hill. Some researchers might get a sample mean that overestimates the mean income of Pleasant Hill. Since each researcher is selecting his or her own group of people, each researcher will get a result that's a little bit different. So these demonstrations help you understand the idea that that the results will vary from one sample to the next. So here's another population of people. Let's pretend that this is another classroom of students who have all taken an exam, and these are their exam scores. Once again, the exam scores are positively skewed. There's a lot more lower exam scores and a lot fewer higher ones. Last time I was taking samples of 3 over and over again and calculating the mean of each sample of 3 people, and we saw that when I used a small sample size of 3, the sample means down here ended up following the shape of the population. If the population was normal, the sample means ended up building up toward a normal shape. If the population was skewed, the sample means ended up forming a skewed shape that looked just like the population. Now I want to show you that if you take samples of 30 people from a skewed population and you calculate the mean of each sample, the sample means will end up forming a roughly normal shape, even though the population is skewed. So I'm going to be taking a sample of 30, calculating the sample mean, taking another sample of 30, calculating the sample mean, and I'm going to do it over and over again, and each time I do it, I'm going to plot the sample mean down here. And all of those sample means that I end up recording should follow a roughly normal shape because of the fact that I'm using a bigger sample size of 30. So, well, here I'm actually using the smaller sample size, so I'll skip over this part because I've already demonstrated that to you. So sorry, I need to scroll back a little bit. Okay, so I randomly select 30 students to be my sample. These are the 30 people that I end up selecting, and I record their exam scores. And this ends up being my data set from the 30 students. I calculate the mean of their exam scores by adding the exam scores and dividing by 30, and I get my sample mean right there. So my sample mean ends up being 65.07, which is pretty close to the mean of the entire population, which is 64.9. Here I take another sample of 30, and you might have noticed that in these demonstrations, I've been reusing people. So just because a person was selected in one sample doesn't mean that they can't be selected again. For example, this person right here was in the red sample, and now they've been selected again in the brown sample. So my samples can overlap with each other. So here's the numbers I recorded from this sample, and this time the sample mean was a little bit lower than the population mean, because the sample mean is 62.7, the population mean is 64.9. Now I repeat my study again. I take 30 more students. I calculate the mean exam score of the sample. I get this sample mean right there, about 63. I keep doing this over and over again with different samples of 30. And so a couple things have changed compared to when I was using a sample size of 3. One thing that's changed is that the sample means are now closer together. They've moved in closer to the population mean. When I was using a sample size of 3, the sample means ended up being pretty spread out over a wide area. But now the sample means are much closer to this population mean of 64.9 right here, with this dotted line. So larger samples tend to be more accurate than smaller samples, which is why each of these sample means, which is a mean of 30 people, is closer toward this population mean right here. So when you use a bigger sample size, the sample means end up being less spread out. They move in closer toward the population mean. And in a later video, we'll talk about that there's actually a word for a technical word for the amount of dispersion in the sample means. It's called the standard error. So if the sample means are really spread out like they were last time with a sample size of 3, the standard error is high. But if the sample means are closer together like they are here, the standard error is low. So the standard error has to do with the amount of dispersion in the sample means. So I told you that the sample means are now less spread out than they were before because the sample size is bigger now. Another thing I want you to notice is that before, with a sample size of 3, the sample means were following a positively skewed shape, just like the population. But now the sample means are following a roughly normal distribution, which I've outlined right here. So when the sample size goes up, the sample means move in closer together, like I said. And if you're sampling from a skewed population, the sample means become less skewed with a bigger sample size. They start to follow a normal curve. Now, what would happen if we were taking... one thing I wanted to mention here is that later on we'll be talking about something called the 95% margin of error, which is the distance from the population mean to the boundary points of where the sample mean will fall 95% of the time. So the sample means are following this bell-shaped curve right here, or a normal curve. If we kept sampling, taking more and more samples over and over again, and calculating the mean of each sample, and we kept on using a sample size of 30 over and over again, the sample means would fall in a certain area 95% of the time. They would fall in this area right here. And they would only fall here 2.5% of the time, and out here 2.5% of the time. And the distance from the population mean to the boundary points of the 95% area is called the 95% margin of error. So this bar is the 95% margin of error. This bar is also the 95% margin of error. And in this situation, these two bars are the same distance. They're the same length because if the sample means are following a normal curve, the two sides are symmetrical. They're the mirror image of each other. And it's actually later we'll talk about how you can only calculate the 95% margin of error if the sample means are following a normal curve, like they are here. If the sample means are following a skewed shape, like they were last time, then the 95% margin of error isn't predictable. And we'll also talk about how when the 95% margin of error is predictable, like it is here, there's a certain formula that has to be used to calculate it. And we'll get to that formula later, but I didn't want to talk about the formula for a 95% margin of error right now. I just wanted to introduce the idea of a 95% margin of error. For right now, I just want you to know that when the sample means are following a normal curve, it is possible to predict where the sample means will fall 95% of the time. Now, I said I was going to tell you what happens when you, if you're sampling from a population that's normal, and you're taking a sample size of 30. This isn't really a very normal population, but it's the best job I could do to make a normal bell-shaped population. Well, first let's think about what would happen if we were taking a small samples of 30. I told you a while ago that if you're taking small samples of less than 30 from a population, the sample means end up following the shape of the population. So since the population is normal, the sample means will also be normal. So I'm just taking more and more samples of 3 and calculating the mean of each sample. So like I said, it follows, the sample means will end up following the shape of the population. So if the population is normal, and you're taking small samples from that population, the sample means will end up being normal, like this right here. And you can calculate the 95% margin of error. And so far we've seen that if you're sampling from a skewed population, the sample means will be skewed just like the population if you're using a small sample size. And the sample means will end up being roughly normal with a bigger sample size of generally 30. They'll be roughly normal even though the population is skewed. If you're sampling from a normal population like you are here, the sample means actually end up being always normal, regardless of what sample size you're using, even if it's a small sample size. So maybe I'll make a quick sketch of what I'm talking about. So if the population is skewed, maybe let's say positively skewed like this, if you're taking samples of less than 30 from the population over and over again, the sample means will end up following a skewed shape just like the population. If you're taking big samples from the population over and over again, and you're calculating the mean of each sample, then the sample means will end up being normal, or roughly normal, even though the population is skewed. That's if you're using a sample size of at least 30 or higher. And the if you used an even bigger sample size, like 50, the sample means would it be even more normal? So actually, if the population is skewed, then the larger the sample size that you use, the more normal the sample means will end up being. So if I used, let's say, a sample size of 100, the sample means would end up being even more normal. If I used a sample size of 200, it would be even more normal. But the sample size of 30 is generally the cutoff point in which the sample means end up following a roughly normal shape, despite the skewness of the population. If the population is normal, and you repeatedly sample from the population, the sample means are always normal, no matter what sample size you're using. Doesn't matter if the sample is less than 30 or above 30. So these will end up being normal. These will also end up being normal. So if I take samples of 3 people over and over again from this skewed population, meaning I take a sample of 3, I calculate the sample mean. I take another sample of 3, I calculate the sample mean. And I do that over and over again. I'll end up getting this shape because I'm using a sample size less than 30. If I take a sample of 30 from this population, calculate the sample mean, take another sample of 30, calculate the sample mean, and do it over and over again, I'll end up getting a roughly normal shape because I'm using a bigger sample size of 30. If I take a sample of 3 from this population right here, the normal population, and calculate the sample mean, and I do that over and over again, meaning I keep taking more and more samples of 3 people and calculating the mean of each one, I'll get a normal shape of sample means, even with that small sample size of 3. If I take samples of 30 from this population over and over again, and I calculate the mean of each one, I'll still get a normal shape. The sample means will still follow a normal shape, because if the population is normal, the sample means always build up to a normal shape, regardless of the sample size. So really, the only situation in which the sample means end up following a skewed shape is if you're taking taking small samples from a skewed population. It's that situation right here. And like I said, this is the one situation in which it's not possible to predict where the sample means will fall 95% of the time, because you don't have a normal distribution. In these other 3 situations, it is possible to predict where the sample mean will fall 95% of the time. You can use, in these other 3 situations, you can use a formula to calculate the 95% margin of error. It tells you the distance from the population mean at the center to the 2 boundary points of where the sample mean will fall 95% of the time. So the 95% margin of error is like a left arm and a right arm, and both arms are called the 95% margin of error because when the sample means follow a normal shape, they're the same distance. this distance right here is the same as this distance right here, so they're both a 95% margin of error. And another way to think about this, which I told you earlier, is that if the sample size is small, the sample means end up following the shape of the population. So this follows the shape of the population. This follows the shape of the population. And if the sample size is big, or meaning 30 or larger, the sample means always build up to a normal shape. So these ones follow the shape of the population. These ones are always normal. Overall, there were three main ideas that I wanted you to learn from these demonstrations. The first idea is that the sample means have less spread than the population that they come from. So notice how all of these sample means have less spread than the individual people in the population. The next point is that the sample means tend to fall within a certain range of the population mean. They tend to not fall too far from the population mean. Every once in a while, you will have an extreme sample mean that's really far above or really far below the population mean, but that doesn't happen very often. The third point is that the sample means follow the shape of the population when a small sample size is used, but the sample means are always have a roughly normal shape when the sample size is large, which is large meaning 30 or larger, 30 or higher. Before we move on, I wanted to tell you what affects the size of the 95% margin of error. When the sample size is larger, the 95% margin of error will be smaller because when you're using a bigger sample size, then the sample means are closer together and they fall inside a narrower area, which means that when a larger sample size is used, this boundary moves in toward the population mean and this boundary moves in toward the population mean. And the area that they fall inside is narrower. So that's why the 95% margin of error shrinks with a bigger sample size. The 95% margin of error also gets smaller when the population has less dispersion. So if this population had less spread to it, and these population members were closer together, then the sample means down here would also be closer together, and the 95% margin of error would be smaller, because the sample means the area that the sample means fall at 95% of the time would be a smaller area. So overall, when a bigger sample size is used, or when the population has less dispersion, the 95% margin of error is smaller because the sample means fall in a narrower area, and the distance from the population mean to these two boundaries will be a smaller distance. So the first part of this video was actually leading up to this topic that we'll talk about in this PowerPoint, which is the topic of sampling distributions. This is an important topic to help us understand the theory behind using data from a sample to reach a conclusion about the population it comes from. First, we need to talk about the idea of sampling variability. Sampling variability is just the fact that different samples give different results. We've already seen sampling variability in the first part of this video because we saw that when you take different samples from a population, the sample mean doesn't always come out to the same number. It changes from one sample to the next. The next term that we'll cover is called a sampling distribution, which is a collection of outcomes calculated with all possible samples of a certain size. And I'll give you some examples of creating sampling distributions. But first, I wanted to start with giving you one more demonstration just to help you get the general idea of what a sampling distribution is. So this simulation is just meant to teach you the idea of a sampling distribution, not how to actually create one. So let's imagine that these are the exam scores of 72 students in a class. It's a population of 72 students, and I wanted to create a sampling distribution of all possible samples of 3 people. What I would need to do is I would need to calculate the mean of every possible sample of 3 people that could be selected from the population. Meaning I would have to calculate the mean of every possible combination of 3 people that could be chosen from the population. And then, once I calculated all of those sample means, I would have the collection of the means of all possible samples of 3 people, and that collection of sample means would be a sampling distribution. So let's think about what are the possible samples of 3 people. Well, here's one possible sample, and it has a sample mean. I should have put an X bar because it's a sample mean, but I just used an X instead. Here's a different possible sample of 3 people, and it has its own sample mean. Here's a different one. Here's one more. So there's all these different possible samples of 3 people that could be selected from the population, and each possible sample has its own sample mean. Some of the possible samples have the same sample mean, and those sample means end up being stacked above each other. For example, these 2 samples both have the same sample mean. Here's another one. All 3 of these samples had a sample mean of 81.7. So what we're actually looking at here is the possible samples that could be selected if someone randomly selected a sample of 3 people from this population. So if a person randomly selected a sample of 3 people from this population, recorded their exam scores, and calculated the mean of the sample, the person would get one of these sample means inside of here. For example, the person might get this sample mean, the person might get this sample mean, the person might get this sample mean right here. Each of these x's is just the mean of a different possible sample of 3 people that could be chosen. So if I get this sample, if I randomly select a sample of 3 people and I end up getting this sample, my sample mean will be about 76. If I randomly select 3 people and I end up getting this sample, my sample mean will be 80. If I get this sample, my sample mean will also be 80. And if I get this sample, my sample mean will also be 80, because all 3 of these possible samples all have a mean of 80. If I get this sample right here, my sample mean will be about 84. So we're just looking at the means of all possible samples that could be selected when a person is selecting a sample of 3 people from the population. Now, there's actually many possible samples of 3 people that could be selected. So I'm not going to be able to calculate the means of all of them. But just, I want you to understand the idea that if I did calculate the means of all possible samples of 3 people and plotted them here, it would be the sampling distribution of the means of all possible samples of 3 people. And actually, every possible sample has its own sampling distribution, because if if I selected a sample of 4 people from this population, my sample would be one of the possible samples of 4 people inside of the sampling distribution of all possible samples of 4 people. If I randomly selected a sample of 10 people from this population, my sample would be one of the possible samples of 10 people inside of the sampling distribution of all possible samples of 10. And the idea of a sampling distribution is important because it shows which sample means are more likely to be found and which sample means are less likely to be found. We can see that if we look at the sampling distribution that's starting to build up here, we can see that the sample means, most of the possible samples have sample means near the population mean, and fewer of the possible samples have sample means further away from the population mean. That means that if a researcher is randomly selecting a sample from a population and calculating the sample mean, the researcher has a good chance of getting a sample mean within a certain range of the population mean that they're trying to estimate. And they're less likely to have a sample mean that's extreme and really inaccurate. So we talked about this idea that when a researcher randomly selects a sample and calculates the sample mean tends to estimate the population mean at least fairly well, meaning the sample mean tends to fall fairly close to the population mean. The reason why that happens is because of the shape of the sampling distribution. So if I wanted to look at all possible samples of 10 people, well, I would need to calculate the means of all possible samples of 10. Sorry, I'll back up a little bit. Here's one possible sample of 10 people that could be chosen. So if I selected a sample of 10 people randomly, and I end up getting this sample, then my sample mean will end up being 80.2. If I end up getting these 10 people, my sample mean will end up being 81, right there. If I get these 10 people, my sample mean will be 82.2, right there. If I get these 10 people, my sample mean will be 78.9. So notice how when you're selecting a bigger sample size, the possible samples have sample means closer to the population mean. Almost all of the possible samples have sample means really close to the population mean of 80. Because remember, larger samples are more accurate. They more accurately estimate the population mean. So when you take a bigger sample from a population, and you calculate the sample mean to estimate the population mean, the possible samples that could end up being selected have sample means that are closer in to the population mean. In other words, the possible samples have accurate sample means. If I get this sample, it'll be pretty accurate. If I get this sample, it'll be pretty accurate. And if I get this sample, it'll be pretty accurate. So when you take a bigger sample from a population, the possible samples move in toward the population mean, and they all tend to have sample means closer to the population mean. That's why a researcher who uses a bigger sample size is likely to get a sample mean closer to the population mean and get a more accurate result. And later on, we'll talk more about how spread out these possible samples are from each other. There's actually a word that's used, there's actually a term for the amount of dispersion that's in the possible samples. When it's called the standard error. When the sampling distribution has high dispersion, meaning the possible samples have sample means that are spread out far away from each other, then the standard error is high. If the possible samples have sample means that are really close to each other, like we see here, the standard error is low. We'll talk more about that a little bit later. First, we need to cover a term called the central limit theorem, which is really just a technical word for something we've already talked about. The central limit theorem says that if the population has a normal distribution, the sampling distribution is always normal. And if the population is skewed, the sampling distribution is skewed just like the population with a small sample size, but is roughly normal with a large sample size. So if the population is normal, the sampling distribution is always normal, no matter what sample size you're talking about, or no matter what sample size you're dealing with. If the population is skewed, the sampling distribution is skewed when you're using a small sample size, but is roughly normal with a large sample size, a third or larger. And I wanted to mention something that tends to cause confusion when people first learn about the idea of a sampling distribution. When students think about the idea of a sampling distribution, they tend to think of it as the distribution of the people inside of a sample. So students tend to think that if you take a sample from a population, then the people inside of the selected sample follow the sampling distribution. They think that it's the distribution of the members of people inside of a certain sample, but that's actually not true. It's not. A sampling distribution isn't a distribution of people. It's actually a distribution of outcomes, or it's actually a distribution of possible samples. So if you take a sample from a population, and you take a certain number of individual people from the population, and you calculate the mean of that group of that sample mean that you've calculated is actually one building block of the sampling distribution. It's just one building block inside here somewhere. So it's actually a distribution made up of all possible samples that could be selected, and each sample is just a building block stacked above its sample mean. So if this right here is, let's say, 70 on the number line, all of the possible samples that have a sample mean of 70 will all be stacked above each other right here. If this is 80, all of the possible samples with sample means of 80 will all be stacked above each other right here. And I'll show you. I'll actually show you a quick demonstration with the website to explain this idea of a sampling distribution. Actually, before I go to the website, I'll make a quick diagram right here. Let's imagine that I'm sampling from the JFK population. I'm interested in the mean. Let's say I'm interested in the mean height of all JFK students. I'm interested in what the mean or average height of the JFK population equals. And I randomly select 30 JFK students to be my sample, I record their 30 heights, and then I calculate the mean of my sample by adding the 30 heights and dividing by 30. The sample mean that I end up calculating will be one sample mean inside of a distribution of all possible samples of 30. And we know that since I'm using a sample size of 30, the possible samples will follow a normal distribution, or at least roughly follow a normal distribution, even if the population is skewed, even if the individual people have a skewed distribution of heights. So here we have the population mean, which is the mean height of the entire university, which I'm trying to estimate. And it's actually unknown, which is why I'm trying to estimate it. But let's pretend that even though I don't know what the population mean equals, let's pretend that it actually is 60 inches. That's the average of the university. If I end up selecting a sample of 30 people, and the mean height of my sample ends up being 60 inches, then the mean of my sample equals the mean of the population, and I've perfectly estimated the mean of the population. And if that's what happens in my study, then my sample mean is directly above 60, right here. It's right on target. But there's more than one possible sample of 30 JFK students that would give me a mean of 60. For example, what I mean is there's other possible samples of 30 out there that would also give me a sample mean of 60, right at the population mean. So all of those possible samples of 30 that have a sample mean of 60 are all stacked above each other right here. So if I get this group of 30 people, my sample mean equals 60, and I've perfectly estimated the population mean. If I get this group of 30, my sample mean is equal to 60, and it's perfectly accurate. If I get this group of 30 people, the sample mean is perfectly accurate. Again, so these are all showing different groups of 30 people. This is a different group of 30 than this is. This is another group of 30. This is another group of 30. It just happens to be that all four of these groups of 30 all have a sample mean of 60. So it's four different groups of 30 people, but they all of them have a mean that's perfectly equal to the population mean of 60. These are four samples, four possible samples that are all perfectly accurate. And if I get one of them, I've perfectly estimated the population mean. But down here, we have all of the possible samples of 30 that would give me a sample mean of 55. And they're all stacked above each other. Here's one group of 30 with a mean of 55. Here's another group of 30 with a mean of 55. Here's all of the possible samples that would give me a mean of 65. They're all stacked above each other too. So here's a group of 30 people with a mean of 65. Here's another group of 30 people with a mean of 65. And what I'm hoping is to get a group of 30 people with a sample mean somewhere in the middle, near 60. Because if I end up selecting a sample somewhere from this middle area right here, then my sample mean is close to the population mean, and I have an accurate result. But if I end up getting a sample of 30 people with a really low sample mean down here, then I have an extreme outcome that's not very accurate. If I end up selecting 30 really short JFK students to be my sample, then my sample mean will be low and it'll be way down here. If I end up selecting a group of 30 really tall JFK students, my sample mean will be really high, and my sample will end up having a really high sample mean out here. So here's a shorter group of 30 people with a low average. Here's a tall group of people with a high average. But if I'm selecting a sample, if I decided to select a sample of 30 people, each possible sample that I could select under this curve is a sample of 30 people. Because if I decided to use a sample of 30, I'm definitely going to get a sample of 30 people. I'm not going to end up getting a sample of 40 people. So like I said, once I've decided on a sample size of 30, then all of my possible samples under the curve are just different possible samples of 30. That's 30, that's 30, that's 30, 30, 30, 30. Now I'll actually go to that website that I was talking about. So here's a website where I can sample from a population. There's what this is showing right here is a population of 18,000 people, and here we see each person's ID number, and here we see each person's sleep time. It's just the number of hours that each person sleeps per night, and it lets me take a sample size and then take a random sample from that population, and then collect data from the sample. So imagine that I want a sample size of 10. It can actually draw 10 people and collect their sleep times as if I had actually done a survey with those 10 people, and then calculates the mean or the average of the sample by adding their 10 numbers and dividing the total by 10. So here we can see that the population is normal or bell-shaped with a mean or average sleep time of 8 hours. So the mean of the entire population is 8 hours, and these are the 10 people in the sample, and this is the mean of that sample. If I click on draw samples again, it'll take another sample of 10 people and record their sleep times. So it's as if I have done the study over again, or someone else has repeated my study with a different group of 10 people. It shows the 10 people inside of a population. It shows the 10 people right here and the mean of the sample. So and it can repeat this process over and over again. And eventually, these will start to form a normal distribution, because if the population is normal, then the sample means end up forming a normal distribution. Also, the sample means are closer together than the individual people are, because notice how the sample means are all most of them are all between 7 and maybe 9, but the individual people are all between 5 and 12. So the sample means are always closer together than the individual people are, and that's especially true if the sample size is large. With a large sample size, the sample means are even closer together. So they're closer together than the population values are, but they do follow a roughly normal distribution. just like the population does. Remember, the population is normal, the sample means always have a normal shape. So let's try to take samples of 30. So what this does is it randomly selects a sample of 30, calculates the mean of the sample, and plots the sample mean right here. So here's the 30 people inside of my newest sample, inside of the population. Here's their sample mean of 7.5, and their sample mean right here. Notice how most of them come from the lower end of the population. So they have lower, most of them have lower sleep times. That's why that's why the sample has a lower sample mean down here that actually falls below the population mean of 8 hours. So here I have a sample with a sample mean that underestimates the population mean, because the sample mean is lower than the population mean. The sample mean is 7.5, the population mean is 8. And every once in a while, sometimes I'll get a sample mean that's above the population mean. For example, this group of people here had 30 people toward the high end of the population, with a lot of people who were getting more sleep, which is why their sample mean ended up being a higher number up here. So since the sample included a lot more well-rested people, their sample mean ended up being a high number up here, above the population mean. But it's still going to build up to form, the sample means will still end up forming a normal distribution, because the population is normal. And if I did this with, if I calculated the means of all possible samples of 30 and recorded each of those sample means as a building block in here, then that would actually be the complete sampling distribution for all possible samples of 30. But if the population is skewed, well, in that case, with if I'm taking a small sample of, let's say, 10 people, I'm likely to get a low sample mean, because I'm likely to get a lot of people from this lower end, because there's a lot of people to draw from down here and not as many people up here. So a lot of the sample means will end up being low. And the sample means will end up forming a skewed shape just like the population. You'll eventually see it, but not quite yet. I can actually do this. It'll actually let me calculate the mean of a large number of samples all at once. So I could do 1,000 samples all at once. It's just taking a second, it'll come up. So the shape still ends up having a positive skewness, just like the population. It's maybe not quite as skewed, but it's still following that positive skewness. Now, And what I can do here is the website actually lets me click on each sample mean inside of here, and it actually shows me the 10 people that are in that sample. So this building block is the mean of these 10. This building block is the mean of these 10. This is the mean of these 10. And if this was showing the means of all possible samples of 10 here, then that would be the complete sampling distribution of the means of all possible samples of 10 people in this population. Now, if I select samples of 30, a bigger sample size, the sampling distribution will be normal, or at least roughly normal, even though the population is skewed. So these sample means will eventually start to form a normal shape. Because if you look at these possible samples of 30 that we're looking at here, a lot of these samples do include a lot of people from the lower end here. There's also, since there's a bigger sample size, there's more higher people mixed in, like there is here, which brings up the sample mean. If each of the possible, so since these possible samples of 30 tend to include higher sleep times mixed in to them, all of those possible sample means aren't quite as low as they were before. That's why they're starting to form a normal distribution. So here we can revisit the samples. We can see that a lot of them have at least some higher people mixed in who bring up the average, which is why the sample means aren't quite so skewed down here as they were before. So now I'll actually move on to the PowerPoint slideshow. This was just meant to demonstrate the idea of the central limit theorem about how the shape of the sampling distribution depends on the sample size and the shape of the population. So now I'm back to the PowerPoint slideshow right where I left off. Now I wanted to go through a few quick exercises of creating a sampling distribution with a small population of only 4 people to help make the idea of a sampling distribution a little bit more concrete. So if I had, imagine that there's a population of 4 people. Maybe it's a family of 4 people or a group of 4 friends, and each person has a value. Maybe this is the height of each person, and let's say that these are the heights of the 4 people. And as a researcher, I want to take a sample of 2 people from this population and calculate the mean height of those 2 people to estimate the mean height of this entire population of 4 people. And I know it doesn't seem realistic, because if the population has only 4 people, why wouldn't I just select all 4 people? But I mean, why wouldn't I just collect data from all population members? But this actually isn't meant to be realistic. This is just meant to be a demonstration of the idea of a sampling distribution. It's just an exercise. So if I selected 2 people out of these 4 and recorded their heights, these would be the possible samples of 2 people that I might end up selecting. I might end up getting person 1 and person 2 and recording their heights. I might get 1 and 3. I might get 1 and 4. I might get 2 and 3. I might get person 2 and person 4, or I might get person 3 and person 4. So if I randomly selected 2 people to be the sample, these are the 6 possible samples, and I'm going to end up getting one of them to be my sample. Each possible sample of 2 people has its own sample mean. You can find it by adding the 2 numbers and dividing by 2. So if you add these 2 heights and divide by 2, you get this number. If you add these 2 heights and divide by 2, you get that number. Remember, x bar is sample mean, so it's just the mean of the sample. And the population mean, which is mu, would be the mean of all 4 population members. If I added their 4 heights and divided by 4, I would get the population mean. So here's the sampling distribution for a sample size of 2. If I'm selecting a sample of 2 people from this population, there's 6 possible samples, and each one has its own sample mean. And these 6 sample means in here make up the sampling distribution for the sample size of 2. And the mean of the entire population, if we calculated it, would actually be 57. That's the mean of all 4 people. If I added these 4 numbers and divided by 4, I would get 57. So we can see that 2 samples have a sample mean that's perfectly equal to the population mean. 2 samples have sample means that are below the population mean. They underestimate the population mean. 2 of the possible samples have sample means above the population mean. So these 2 samples overestimate. So we're just seeing the idea of sampling variability right here. Here, if I was taking a sample of 3 people from this population, recording their 3 heights, these would be the 4 possible samples. I would end up getting one of these 4 possible samples to be my actual sample. And the way I created these possible samples is just by leaving one person out of each sample. So here I left out person 4, here I left out person 3, here I left out person 2, and here I left out person 1. That's how I created these 4 possible samples. Each possible sample has its own sample mean. You can find it by adding 3 numbers and dividing the total by 3. So if I selected 3 people from the population, recorded their heights, and calculated the sample mean as an estimate of the population mean, then one of these 4 sample means would end up being my sample mean that I actually used to estimate the population mean. This might be my sample mean if I get sample 1. This will be my sample mean if I get sample 2. This will be my sample mean if I get sample 3. So here's the sampling distribution. If there's 4 possible samples, and the means of those 4 samples that I listed out here make up the sampling distribution. All I did was I took the 4 sample means over here and listed them in a column. So these 4 sample means all make up the sampling distribution. All 4 of these x bars make up the sampling distribution over here. Now let's discuss the mean of standard deviation of a sampling distribution, because a sampling distribution is really just a list of numbers. So any list of numbers has a mean and standard deviation. The mean of the sampling distribution is always equal to the mean of the population, regardless of the sample size. That's something we'll look at in a second. So the sample means are always centered at the population mean. So let's take a look at that. Here, if we add the 4 values in the population and divide by 4, we get the population mean, which is 57. The population has a mean height of 57. If we add the 6 sample means over here and divide the total by 6, we get the mean of the sampling distribution, which is also 57. So I said that the population mean and the mean of the sampling distribution always come out to the same number. And the symbol for the population mean is mu, but the symbol for the mean of the sampling distribution is actually mu x bar, because it's the mean of all of the sample means. Remember, x bar is sample mean. So here, let's look at a visual of this. Here's the 4 heights of the 4 population members with the population mean at the center. Here's the 6 sample means in the sampling distribution with the mean of 57 at the center. So the population is centered at 57 because that's the population mean. And the 6 sample means are also centered at the population mean. And we can see that so this side of the sampling distribution has sample means that underestimate the population mean. This side of the sampling distribution has sample means that overestimate the population mean. But it's roughly half underestimate and half of them overestimate because the population mean is at the center. Now let's look over here. If we add these four numbers and divide by 4, we get the mean of the other sampling distribution, which was the means of all possible samples of 3 people. Once again, the mean of the sampling distribution equals the population mean. I said that the population mean and the mean of the sampling distribution are always the same number, regardless of what sample size you're dealing with. So it's 57 again. Once again, you can see that just like how the population has the population mean at the center right here, the sampling distribution of sample means also has the population mean at the center. But since we're dealing with a sample size of 3 now, since each of these sample means is now a mean of 3 people instead of just 2, the sample means are now closer together. They're more packed in toward the population mean of 57. So the population had the most spread. The means of the samples of 2 people had less spread, and the possible samples of 3 people, their means had the least spread of all. So when we go from here to here to here, we're looking at less spread. But all 3 of them have 57 and have a population mean of 57 at the center, because they all have the same mean of 57. Like I said, they don't all have equal dispersion. This has the most dispersion. This has the least dispersion. And there's actually a value that measures the amount of dispersion or the amount of spread in a sampling distribution, and it's called the standard error. So, and I'll talk about the standard error next. The standard error is really just the standard deviation of the sampling distribution. Remember, the standard deviation measures the spread of a set of numbers, so the standard deviation of the values in a sampling distribution have a special name called the standard error, even though it really is just a standard deviation. So the standard deviation of these 6 sample means would be called a standard error, because these 6 numbers make up a sampling distribution. The standard deviation of these 4 numbers would also be called the standard error. So the standard deviation of the sampling distribution is the standard error. It measures how spread out the sample means are from each other. So if we actually wanted to calculate the standard error, we would just plug in the standard deviation formula and just get our answer just using the standard deviation formula. This right here would be the standard error of these 6 sample means in the sampling distribution over here. And it's really just a standard deviation, but it's called the standard error. It's called a standard error because it's not a standard deviation of people, it's a standard deviation of sample means. These 6 numbers over here are all just sample means. If we plugged in the other sampling distribution, which included the means of the 4 possible samples of 3 people, it would be another standard error. Remember, this was the mean of 3 people, this was the mean of 3 people, and this was also the mean of 3 people, and this was the mean of 3 people. The standard deviation of these 4 values would also be called the standard error. So it's called, the standard error is 0.7. So here, well, the standard deviation of the people in the population is just called the population standard deviation sigma, and it's 2.24. So these four heights have a standard deviation of 2.24. The standard deviation of these 6 sample means is called the standard error, and it came out to 1.3. The standard symbol for standard error is sigma x bar, because it's the standard deviation of the sample means. These 4 values had a standard error of 0.7. And you can probably see why these 6 numbers had a higher standard error, and these 4 numbers had a lower standard error, because these 6 sample means of all possible samples of 2 people are more spread out, so they have a bigger standard error. These 4 sample means of all possible samples of 3 people have less spread, which is why they have this smaller standard error. So when the sample size goes up from 2 to 3, the standard error drops, because the sample means move in closer together. And the reason why this idea of a standard error is important is because when a researcher takes a sample from a big population and calculates the sample mean to estimate the population mean, and if the researcher uses a small sample size, the means of all of the possible samples will be more spread out with a bigger standard error, and the researcher is likely to get a less accurate sample mean further from the population mean at the center. But if the researcher takes a bigger sample from that population and calculates a sample mean, then all of those possible samples that could be selected have sample means that are closer together, more moving in closer toward the population mean. So the researcher is likely to get a more accurate sample mean in that situation. So if I was interested in estimating the mean income of Pleasant Hill, and I take a sample of 10 people, and I calculate the mean of and I record their 10 incomes, and I calculate the mean of my sample to estimate the population mean, the standard error will be big, because all of the possible samples of 10 people that I could get they'll have widely different sample means, like we see here, and I could get a sample mean that's way off from the population mean. But if I take a sample of, let's say, 100 people from Pleasant Hill and record their incomes, and I calculate the sample mean, the mean of my 100 people is likely to be more accurate, closer to the population mean, because all of those possible samples of 100 that I could get from Pleasant Hill will have sample means that are closer together and close to the population mean that I'm estimating. So I'm likely to get an accurate sample mean in that case. So when I use it in a study, when I use a bigger sample size, the standard error is smaller, because the possible samples that the researcher could get have sample means that are closer together and closer to the population mean. So you want to use a big sample size if you can, so that the standard error will be small, and you're likely to get a sample mean close to the population mean. You don't want the possible samples to have high dispersion like they have here. You want them to have low dispersion like they are here. Also, if a study is repeated over and over again, and a different result is calculated each time, then, well, if a small sample size is used and the standard error is big, what ends up happening is the results change a lot from one study to the next. They bounce around a lot. So if I keep sampling 2 people from here over and over again, and I calculate the mean, and each time I take 2 people, I calculate the sample mean, my sample means will change more from one outcome to the next. Sometimes I'll get 55. Sometimes I'll get 59 up here. Sometimes I'll get 55 again. Sometimes I'll get 56 again. But with a if you use a bigger sample size and the standard error is smaller, then the results don't change as much from one study to the next. Because if I kept on sampling 3 people from this population over and over again and calculated the mean each time, sometimes I'd get this, sometimes I'll get this, but overall, my results will be pretty more consistent from one outcome to the next. It'll be more like this. Because if the possible samples are closer together, like they are here, the results will be more similar from one study to the next. If the possible samples are more spread out, you have less consistent results from one study to the next. So when the sample size is bigger, the standard error is smaller, which means the possible samples have sample means that are less spread out. And also, when the study is repeated over and over again, the results will be more consistent from one outcome to the next. And I showed you a couple examples of calculating a standard error with the standard deviation formula, but in an actual study, you can't calculate the standard error that way because you don't actually have a list of all possible samples like I did. You don't know what all those possible samples are, so there's actually a formula that's used in an actual study to get the standard error. What it is the standard deviation of the people in the population standard deviation, divided by the square root of the sample size you're using. The sample n is a symbol for sample size. So if I'm taking a sample of 30 people from the Pleasant Hill population and recording their incomes, and I'm calculating the sample mean to estimate the population mean. And like I said, if I'm taking 30 people, if I divide the standard deviation of Pleasant Hill incomes, the population standard deviation, by the square root of 30, which is the sample size that I'm using, I will actually get a standard error of my study, which is the standard deviation of the means of all possible samples of 30 that I might end up selecting to be in my study. In other words, I'll get the standard error of the sampling distribution that I'm drawing from, which in my case would be all possible samples of 30. And if I'm, once again, I want the standard error to be small because that means that the possible samples are more similar and more accurate. Here's one more short slideshow that should help you understand the idea of a sampling distribution. Imagine that this is a population of 5 people, and that each number is the person's age. So we have a 20-year-old, a 22-year-old, a 24-year-old, a 26-year-old, and a 28-year-old. And the mean age of this population is 24. So if you added the 5 ages and divided by 5, you would get the population mean of 24. Now let's imagine that I want to take a sample from this population and record the ages of the people in my sample. And maybe I want to take a sample of 2 people and record their ages. So I decide that I want to randomly select 2 people from the population. Well, imagine that there's a certain button I can press that creates all possible samples of 2 people and places each of those possible samples above its sample mean. So here's person 1 and person 2. They're a possible sample of 2 people. Person 1 and person 2 their ages are 20 and 22, so they have a sample mean of 21. That's why they're right here. So they're the sample with the lowest sample mean. That's why they're all the way down here. Person 4 and person 5 are also a possible sample that I might get. Their ages are 26 and 28. And the mean of their 2 ages is 27. If you added their 2 ages and divided by 2, you would get 27 right here. So these 2 people are the lowest sample in the sampling distribution because they have a mean of 21. These 2 people are the highest sample in the sampling distribution because they have a mean of 27. Now let's look at these 2 possible samples right here. Person 1 and person 4, their ages are 20 and 26, so they have a mean of 23. If you add 20 and 26 and divide by 2, you get 23. But person 2 and person 3, their ages are 22 and 24. They also have a mean of 23 because 22 plus 24 divided by 2 is 23. So here we have one possible sample with a mean of 23, and here we have another possible sample with a mean of 23. These 2 samples both have a mean of 24, and these 2 samples both have a mean of 25. So when I randomly select my sample of 2 people, one of these possible samples will end up being my actual sample. So maybe I end up selecting person 4 and person 5, and I end up recording their ages, and my sample mean ends up coming out to 27. And this ends up being my data set because I recorded the ages of those 2 people. So you can imagine a sampling distribution as kind of like a gumball machine where one gumball will end up falling and end up being your selected gumball. Now imagine that instead of selecting a sample of 2 people from the population, I want to select 3 people. So what I do is I press a button that says I would like a sample of 3 people, and then it sorts out all the samples into all possible samples of 3 people, all possible combinations that could be selected, and each one ends up being stacked above its sample mean. So here's one possible sample of 3 people, person 1, 2, and 3. Their ages are 20, 22, and 24, and those 3 people have a mean of 22. The mean of their 3 ages is 22. That's why this sample is above 22 right here. So they're the lowest possible sample. Person 3, person 4, and person 5, their ages are 24, 26, and 28, so they have a mean of 26. They're the highest possible sample in the sampling distribution. And when I randomly select a sample of 3 people, one of these samples will end up falling to be my actual sample that I actually select in my study. So maybe I end up selecting person 1, person 4, and person 5 to be my sample, and I record their ages, and my sample mean turns out to be 24.7. And this ends up being my data set that I've recorded from those 3 people. So this is just another quick demonstration to help you understand what a sampling distribution is.